The Mediterranean basin, a region bathed in sunshine and steeped in history, is renowned for its olive groves. These ancient trees produce the liquid gold we call olive oil, a staple in kitchens around the world. But this culinary treasure comes at a cost. The process of extracting oil from olives generates a significant amount of wastewater, known as olive mill wastewater. This effluent, rich in organic matter and dark in color, poses a serious environmental threat. Traditional methods of disposal, often involving direct discharge into rivers or onto land, have devastating consequences. Waterways become choked with organic load, depleting oxygen levels and harming aquatic life. Soils suffer from reduced fertility and contamination. The very landscape that nurtures the olive tree is jeopardized by the byproducts of its bounty. The challenge is clear: to find sustainable solutions for treating olive mill wastewater and mitigating its environmental impact. This is not just an environmental imperative, but also an economic one. By transforming this waste stream into a valuable resource, we can unlock new possibilities for a more sustainable future. The quest for innovative treatment technologies is driven by the urgency to protect our planet and ensure the longevity of the olive oil industry itself. It is a journey that demands ingenuity, collaboration, and a deep respect for the delicate balance of nature. In the heart of the olive mill wastewater problem lies an ingenious solution, harnessing the power of nature itself. Within this wastewater, a hidden army of microorganisms exists, perfectly adapted to breaking down the complex organic compounds that pose the greatest environmental threat. These indigenous microorganisms are the unsung heroes of bioremediation. Aerobic biological treatment provides the ideal conditions for these microscopic allies to flourish. By introducing oxygen into the wastewater, we stimulate the growth and activity of aerobic bacteria. These tiny workhorses consume the organic matter, effectively digesting it and converting it into less harmful byproducts. This natural process, similar to composting on a grand scale, offers a sustainable and efficient way to reduce the environmental impact of olive mill wastewater. By cultivating the right conditions for these indigenous microorganisms, we can accelerate the breakdown of pollutants and pave the way for further treatment. The beauty of this approach lies in its elegance. We are not introducing foreign substances or relying on complex chemical reactions. Instead, we are simply empowering nature to heal itself, utilizing the very organisms that have evolved to thrive in this environment. It is a testament to the remarkable ability of nature to provide solutions even to the most challenging problems. While aerobic biological treatment lays the groundwork for olive mill wastewater purification, it is often not enough to achieve complete mineralization and decolorization. This is where a cutting-edge technology comes into play: electrochemical oxidation over a boron-doped diamond anode. This process introduces a controlled electrical current through the wastewater, generating highly reactive hydroxyl radicals at the surface of the anode. These radicals act like tiny but powerful oxidizing agents, attacking and breaking down even the most stubborn organic molecules resistant to biological treatment. The boron-doped diamond anode is particularly well suited for this task. Its exceptional hardness, chemical inertness, and wide electrochemical window make it a highly efficient and durable electrode material. By combining the power of electrochemical oxidation with the efficiency of aerobic biological treatment, we can achieve a synergistic effect. The biological stage removes the bulk of the organic load, preparing the wastewater for the more refined oxidation process. This two-pronged approach ensures a higher degree of purification, bringing us closer to the goal of transforming olive mill wastewater from a pollutant into a valuable resource. Section 4. Finding the perfect balance, comparing reactor designs and modes. The success of any wastewater treatment system hinges on optimizing the treatment process. In the case of OPW, various reactor designs and operating modes have been explored to maximize treatment efficiency. Suspended growth reactors, such as sequencing batch reactors, maintain microorganisms freely suspended in the wastewater. These systems offer flexibility in operation and can handle variations in influent characteristics. On the other hand, Attached growth reactors, like biofilters, provide a surface for microorganisms to attach and form biofilms. This configuration promotes higher biomass concentrations and can enhance treatment efficiency. Operating modes also play a crucial role. Batch mode involves treating a fixed volume of wastewater in a discontinuous manner, while continuous mode allows for a steady flow of wastewater through the system. Recirculation of treated effluent within the system can further enhance treatment by increasing contact time between microorganisms and pollutants. The choice of reactor design and operating mode depends on several factors, including the characteristics of the OPW, the desired treatment goals, and the available resources. Pilot-scale studies are often conducted to evaluate different configurations and identify the most effective approach for a given scenario. Section 5. A measure of success, CODI and phenol removal rates. The effectiveness of any OPW treatment system is ultimately judged by its ability to remove pollutants and render the wastewater safe for discharge or reuse. Two key indicators of treatment success are chemical oxygen demand, or COD, and phenol removal rates. COD represents the amount of oxygen required to chemically oxidize organic matter in the wastewater. High COD levels indicate a high organic load, which can deplete oxygen in receiving water bodies and harm aquatic life. Phenolic compounds present in OPW are particularly toxic and contribute to its characteristic dark color. Studies have demonstrated the effectiveness of combining aerobic biological treatment with electrochemical oxidation in achieving high COD and phenol removal rates. Biological treatment can achieve significant COD reduction, typically in the range of 70 to 90%, depending on the operating conditions. Subsequent electrochemical oxidation further polishes the effluent, achieving near-complete mineralization of organic pollutants and significantly reducing COD levels. Phenol removal follows a similar trend. Biological treatment effectively removes a portion of phenolic compounds, while electrochemical oxidation targets the remaining recalcitrant molecules, achieving high removal efficiencies. These results highlight the synergy between these two treatment approaches in tackling the complex pollution profile of OPW.